Hello, I'm Nurul Iziani. So I would like to present on the MC2 system optimization project simulation result. So in this project, we are required to design two dot product functional unit, which is one is a baseline design, which is just a serial computational design, and another one is a optimized design. So I will show you firstly I will go through the baseline design and the test bench and the simulation. So basically the design of the dot product is we will have input array of 16 elements A and B, and we will times them together and accumulate the result in as the output S. So the test bench is like this. So we will define as usual, we define the DUT that we want to test with, and then we generate the clock. So in this case, I'm generating a 10 nanoseconds period clock, and initially we will set everything to reset, and after 10 delay we will set reset by 0, so and begin the computation. So here I initialize the value of array 16 array elements for A and B, and also here is the our reference results, which is computed by software, which we will later compare with the actual output from the DUT, which is our design. So I have compiled the simulation. Let me run again. Okay. A bit slow. Okay, so this is the behavior simulation from Xylings tool. As you can see, the baseline design is doing everything in series. So you see the value of S here, increment by each clock cycles. So it will sum up all the dot product for all the multiplications result from array A and B, and finally we will get the result of 816, which equal to the result of our test bench reference value. So the behavior of this the functionality is correct, yeah. And then I have also run implementation of the synthesis and implementation of this design. So basically this is only required at TLUT's 15 flip-flops and 172 input output pins with 4.73 nanosecond of slack, and nothing is and each of the and there is no negative slacks reported, so timings are met. We will discuss further on the results, and this is the power consumption, which is it requires 0.023 watts of dynamic power. Okay, so quickly jump into the optimized result. So this is the optimized results that optimized design that I have come with. So I'm using partial loop unrolling with n equal to 2, and I am also using pipelining for my optimization technique. So as you can see, I need to register. I need to add 1, 2, 3, 4 more registers to hold my data at each clock cycles, So P1A will get the value for element A and B, multiplication of element A and B of the first count, and part line B will hold the multiplication value of element A and B at the next count. And then all of this is summed together, using summation at the second part line, and this second part line will be summed up together with the previous accumulation results, and we will count plus by 2, which by we are using partial loop rolling, as we are processing two data together in parallel. And then there are some logic here to ensure that the functionality is correct whenever that the current count equal to 16. So we will still continue to execute or to calculate the value, because there are still some data available in the part lines, and we count by 1, plus by 1, and then if there is no more result, then we put result to compute, then we put done equal to 1. Yeah, so this is my optimized design. So test bench will be the same, so I'm using the same test bench as I used previously in the previous baseline design. Okay, so this is I'm going to show you the timing diagram of the optimized designs. Okay, so as you can see here, actually there are P1A, P1B, P2A, and S signal here. So you can see that P1A and P1B is if you remember from the code just now, is multiplying two data in element A and B together. So P1A processing the first count and P1B processing the next count. So it will do this process parallelly, and then pass the data to be summed together in P2A in the register P2A. So 16 plus 30 in the next clock cycle will become 46, and then 46 will accumulate together with the previous S signal results, which is the summation of the accumulation of the dot product. So 46 carried over to the next clock cycle become 46, and so on. So and then in the meantime, while processing the summation, the next clock cycle already processing the next data of element A and B. So it goes on, and we will get the correct output result when done is equal to 1, which is 816, equal to the reference results of the test bench. And then let me show you the implementation. After I run implementation, there is a double of the utilization for LUT here, 168 compared to 80 from baseline design, and flip-flop is also double from I think 18 into 46. So because we are using more pipeline registers compared to the baseline design to allow for parallelization. And however, there is improvement in the power consumption, where the dynamic power compared to baseline design is reduced to 0.007 watt only, compared to 0.0023 watts of the baseline design. And the delay is also lower compared to the baseline design. So let me show you a table of the comparison. Yeah, so basically as you can see, the results of the optimized design here is better compared to the baseline design by improvements of at least more than 7% of value here. However, as we actually expected, is the error will be degrading from the baseline design, because we are using a lot more registers compared to just serial design. Yeah, so I think that's all for my presentation. Thank you.